Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this second video on vectors. So there are a few definitions on your screen that you need to know that are very important, and we'll go through them. So we're looking at linear combinations of vectors. So if you have a set of vectors, it doesn't matter how many you have. The set that I listed here has n vectors. A linear combination is just an expression where it's something times the first vector plus something times the second vector plus something times the third vector, and so on. So each of those somethings here, which I've denoted as a's, is just a real number. So it's just a number times the first vector plus a number times the second vector, and so on. So here the x's are vectors and the a's are scalars. So we're going to look at the span of vectors, which if I have a set of vectors, the span is just the set of all possible linear combinations of those vectors. Now we also need to know something very important from this video, which is the concept of linear independence. So if you have a set of vectors and any vector in that set cannot be written as a linear combination, which means this, of the preceding vectors, then it's linearly independent. So that means that if I have a given vector in the set, I can't write it as something times the first vector plus something times the second vector, and so on. And if all of the vectors in a set are linearly independent, then we say the set is linearly independent. Okay, so let's look at some examples where we can understand what these might mean. So please pause and copy these definitions down if you need. So we're going to investigate the concepts on the previous slide by looking at these two sets here, each of which contains two vectors. So let's look at the first set, S1, containing the vectors 1, 1, and 2, 2. So any linear combination of these two vectors will have the form some scalar number times the first vector plus a scalar times the second, right? So if I go ahead and actually figure this out, I'll get the first vector plus the second vector. I end up with a plus 2b for both the first and second elements. So any linear combination of these two vectors gives me another vector in two dimensions in R2, where the first and second elements are the same. So if I look at the span of S1, the span of the vectors in S1, it's saying which vectors can be written as a linear combination of the vectors in S1. Which vectors can be written in this form? And as I've seen here, the only vectors that can be written in this form are vectors where the first entry, I'll just call it alpha, is the same as the second entry. So it turns out that the span of these two vectors is one-dimensional. If you were to, say, graph all of the vectors that are in the span of S1, it would be a two-dimensional line. It'd actually be the line like y equals x, the line where the y and the x coordinates are equal. So what this means is I can't write any vector in R2 as a linear combination of these two vectors. The only vectors that will be in the span are ones where both entries are equal. So for example, 7, 7 would be in the span of S1, but something like 8, 5 would not. I can't write this vector as a linear combination of the two vectors in S1 because it doesn't have the same x and y value. So the set S1 does not span R2. It doesn't span as much as it could. The reason for this is it turns out that the two vectors are not linearly independent. So we have to be a bit careful here. When you have two vectors and only two vectors, the set is linearly independent if neither vector is a scalar multiple of the other. But what you can see here is the first one here, there's no vector before it, so we count that as linearly independent. But the second vector here is just a scalar multiple of the first vector. So it is a linear combination of the first vector. So it is not linearly independent. So because not all vectors in S1 are linearly independent, the whole set is not linearly independent. It is linearly dependent. So we say it like this. S1 is not a basis for R2. So what that means is I can't write every vector in R2 as a linear combination of the vectors in S1. In other words, not every vector in R2 can be written as a linear combination of the two vectors in S1. So this concept is very important when we look at linear transformations. We're also going to look and come back to, again, systems of linear equations, simultaneous equations. So asking whether a vector is in the span of another set of vectors turns out to be the same as asking, is there a solution to a particular set of simultaneous equations? We'll look more at that later. So all you need to know now is that a basis for R2 or R3 or R4 or whatever is a set of linearly independent vectors such that every vector from R2, R3, R4 or whatever can be written as a linear combination of the vectors in the basis. Okay, so let's look now at set S2. So a linear combination of the vectors in S2 will look like this. It'll be some scalar times the first vector plus some scalar times the second vector. Again, there's no reason that A and B have to be equal or whatever. So if I add these together, I get 3A plus 4B and minus 2A minus B, right? So this one's a lot less obvious. Is it possible that I can write any vector in R2 as a linear combination of these two vectors, right? So what that is saying is that if I have the equations, let's say 3A plus 4B and minus 2A minus B, if I make them equal to some number in R2, let's just call them C and D, will there always be a unique solution? Right? So that's actually not an easy question to answer. It turns out the answer, though, is yes. There will always be a solution to this system of equations. Why is that? Well, as we were talking about in a previous video, it's because neither equation is a scalar multiple of the other. So if I were to graph these lines A and B, I can replace the x-axis with A and the y-axis with B. These lines wouldn't be parallel, they also wouldn't be the same line. And you can see that here. Neither vector is a scalar multiple of the other. So what that means is this set is actually linearly independent. So because this set is linearly independent, I can write any vector in R2 as a linear combination of these two vectors, because if I just replace this with C and this with D, C and D will always have a solution because neither vector is a scalar multiple of the other. So in this case, we say S2 is a basis for R2. So that means that any vector in R2 can be written as the linear combination of the vectors in S2. So if you're trying to find a basis for R2, R3, R4, whatever, if you're trying to find a basis for Rn, all you need is n vectors that are linearly independent. And if they are, they will form a basis for Rn. If they are not linearly independent, if there is just one vector in the set that is linearly dependent, then the whole set will not form a basis. As we saw here, there was one vector that was linearly dependent, therefore the whole set is linearly dependent, therefore the set does not form a basis for R2. Okay, so that's all well and good for 2 dimensions. Let's look at an example in R3. So we're going to have a look at this question here. So we have a set containing 3 vectors, and we're asking, does it form a basis for R3? In other words, can I write any vector in R3 as a linear combination of the 3 vectors here in this set? Now, because there are 3 vectors and R3 is 3-dimensional, each vector has 3 entries, that means to determine whether or not this set is a basis, I only need to determine whether or not this set is linearly independent. If this set is linearly independent, then I will be able to write any vector in R3 as a linear combination of these 3 vectors. Now, it was easy on the previous slide because we had a set with 2 vectors. Dealing with 2 vectors is easy. In order to determine whether the 2 vectors form a linearly independent set, all you need to do is check whether the second vector is a scalar multiple of the first, and that's really easy to do. This one is not so easy, because linearly dependent doesn't mean that any vector is just a scalar multiple of the other vectors. It means that it can be written as a linear combination of the others. So we don't know, can we write, something times this plus something times this to equal something times that? That's what we have to check. Now, we don't want to go through and check each vector individually and see whether or not it is linearly independent. Instead, what we can do is use this trick. So we can use this trick here to determine whether or not the set is linearly independent. I set up the equation something times the first vector plus something times the second vector plus something times the third vector equals 0. Equivalent to asking whether one or more of the vectors is linearly independent is seeing whether or not there is a non-trivial linear combination that equals 0. So trivial means that all the weights are 0. So if I have the equation a times first vector plus b times second vector plus c times third vector equals 0, a equals b equals c equals 0 is a solution. It will always be a solution regardless of whether the set is linearly independent or not. It is actually a trivial solution because it's kind of really obvious. But if this is the only solution to this set of equations, if the only linear combination of the 3 vectors that equals 0 is when all the weights or the scalars a, b, and c are 0, if that is the only solution, then the set is linearly independent. If there is one non-zero solution, one solution where either a, b, or c does not equal 0, the set will be linearly dependent. Okay, so that's a trick we can use to check for linear independence. And it turns out to be a little easier to do than trying to take each vector one by one and seeing whether or not it can be written as the linear combination of the others. So let's look at this equation here. So if I actually go through and multiply each vector by the scalar, I get a plus 4b plus 10c. So that is the first entry of the vector. The next one will be 0 times a, so I can leave that out. So I have minus 4b minus 12c, and then minus a plus 4b plus 14c. I want to see what values of a, b, and c can make this equal to the 0 vector. 0, 0, 0. And I should have pointed that out here. By 0 here, I mean you can't have a set of vectors adding to a scalar. I mean the 0 vector, the vector where all entries are 0. So, hopefully this is looking familiar. This is just a set of simultaneous equations, 3 equations, and 3 variables, A, B, and C. We know how to solve an equation like this. We set up our equation and in an augmented matrix and use row reduction or Gaussian elimination. So we set up our matrix like this, and you can see this coefficient matrix is just all of these vectors put together. Each vector is a different column of our coefficient matrix. So we perform the row reduction algorithm until we either get a row of zeros or we get in row reduced echelon form. So I'm just going to skip over that part and give you the answer because you already know how to do that. So in row reduced form, I end up with a matrix that looks like this. So remember, if I have a row of all zeros, that means there are infinitely many solutions to this equation. So A equals B equals C equals 0 cannot be the only solution because there are infinitely many solutions. So that means there is at least one other solution where A or B or C does not equal 0. What that means is the set is linearly dependent. So that isn't at all obvious from looking at it, but the way I set it up is that this vector here is 2 times the first vector plus 3 times the second vector. So it can be written as a linear combination of the other 2 vectors, but again, that isn't obvious just from looking at it. What we instead do is see whether there is another solution to this equation, A times first vector plus B times second vector and so on. We see if there is another solution other than A equals B equals C equals 0. We see if there is a non-trivial linear combination of the 3 vectors that equals 0. And we found out that there is. There are actually infinitely many solutions, infinitely many linear combinations of these 3 vectors that result in the 0 vector. So that means because this set is linearly dependent, does this set form a basis? No. That means that there will be some vectors in R3 that you cannot write as linear combinations of these 3 vectors. For example, the vector 1, 2, 1 cannot be written as a linear combination of these 3 vectors. Therefore, 1, 2, 1 is an example of a vector that is not in the span of these 3 vectors here. And because there are some vectors not in the span, that means that these 3 vectors do not span R3. Therefore, they do not form a basis for R3. Alright, I know this has been some heavy stuff and a long video. Best of luck. This is the luckiest maths teacher in the world. Have a great day.